What's up, bitches? Does it seem like everybody and their grandma is talking about Bitcoin nowadays, but you still don't have a clue? Then this video is for you. Alright, so what is Bitcoin? Bitcoin was first introduced by Satoshi Nakamoto towards the end of 2008 in a white paper titled Bitcoin, a peer-to-peer electronic cash system. Now, a white paper is just a fancy word for an article in which Satoshi described how the Bitcoin system works. And a peer-to-peer electronic cash system just means that the Bitcoin system allows one person to send electronic cash, in this case Bitcoin, directly to another person without a third party as an intermediary. Then Satoshi published the first implementation of this electronic cash system as an open source software. Now, open source software just means that the whole program, every single line of code that makes up the Bitcoin software, is available freely on the internet to anyone. You can just go to github.com/Bitcoin and download the software. Now, this might seem trivial, but it has some important consequences. First of all, it means that it does not matter who Satoshi is, because even if Bitcoin was developed by the CIA, the Chinese, the Russians, or some malicious hackers, it doesn't matter, because everyone who downloads the software can see every single line of code and check if there are some crazy backdoors that could steal your coins or whatever. And since thousands of developers have already done that and not found any malicious lines of code, we know that there is no way for anyone to manipulate Bitcoin. So next time Jamie Dimon tries to take your Bitcoin from your lettuce hands, just go to GitHub and check the code. There are also other benefits to open source software, for example that anyone in the world can help to improve Bitcoin. But now we want to focus on what the software actually does. So if you download Bitcoin and execute it on your computer, the software will talk over the internet with all other computers that are running the Bitcoin software. All these computers are called nodes, because if you visualize the network, it will look something like this graph, where every node represents a computer running the software, and every line represents a connection of two nodes, so computers running the Bitcoin software talking to one another. And basically all these nodes do is keep a file called a ledger that keeps track of every transaction that has ever been made on the Bitcoin network. So for example, you can see there was a transaction 0 where A received 50 Bitcoin. Then there was a transaction 1 where A sent 10 Bitcoin to B, followed by transaction number 2 where B spent those 10 coins by sending them to C. This way, every node can always verify how many Bitcoins someone owns. You can simply sum up all the coins in all the transactions to get the final balance. For example, we know that A received 50 coins and then spent 10. So at the time of transaction number 4, we know that A owns 40 coins. This is important because it allows anyone to make sure that no one can cheat. For example, if in transaction number 4, B tried to buy something from you with their Bitcoin, you could just simply verify that right now, at this time, B does not own any Bitcoin, because those 10 that he received in transaction number 1 were already spent in transaction number 2, leaving him with a final balance of 0 Bitcoin. Alright, next we can compare the Bitcoin system with the traditional payment system. So right now on the left side, if Alice was to buy something at a store, the store would simply check with the bank if Alice has sufficient funds to buy the product, and if so, the bank would on its ledger subtract the amount from Alice's account and add it to the balance of the store. Now, in the Bitcoin system, there is no third-party intermediary needed, because the store has its own node. And so if Alice wants to buy something, the store can just simply check if Alice has sufficient funds. The store can simply sum up all the transactions in which Alice was involved, and if the final balance is large enough, it can sell Alice the product. This is what people mean when they say that Bitcoin is peer-to-peer. Alice and the store can simply finalize a transaction on the Bitcoin network without any involvement of a third party. Now, this might not seem important to you, but just imagine if the bank stopped processing transactions of your wife's OnlyFans account. Suddenly Bitcoin would seem much more interesting, wouldn't it? But jokes aside, Bitcoin can actually be a lifesaver for people living under oppressive regimes that would not allow them to just open up a bank account. Think of the people that were a little bit too much pro-democracy. Do you think the CCP will still allow them to have a bank account? Or think of the women in Saudi Arabia that still need the approval of their husband to open up a bank account. We should also not forget that shit can hit the fan even in Western countries. What will you do if you want to get your money, but you get greeted by these guys? And then there are all the people that don't even have a bank account. They have to carry all their money in cash or store it under their mattress where it can be easily stolen. So next time Pocahontas tries to tell you that Bitcoin is only for criminals, tell her to STFU. Alright, now that we have seen that Bitcoin being a peer-to-peer network has some important consequences, let's have a look how such a peer-to-peer transaction works in a bit more detail. Let's imagine that Alice wants to send Bob 1 Bitcoin. To do that, she has to create a transaction. This transaction is then broadcasted to the network, which means that all the nodes send the transaction to their peers, which are the other nodes that they are connected to, and they can all update their ledger with the new transaction. Now, of course, in the real ledger, you don't use nibs, so you can't send some Bitcoin to Shadowy Supercoder 69, but you have to send Bitcoin from and to addresses. Bitcoin addresses look like random strings of numbers and letters, but more on that later. In this example, you can see that Alice has an address which is 1 G D capital K, 9, and so forth. So if Alice wants to make a transaction, she has to reference her address as an input, and she must have received at least the amount of Bitcoin that she then wants to send. As the output, she has to specify the address of Bob and the amount of Bitcoin that she wants to send. If she wants to send one whole Bitcoin, she will send 100 million Satoshis, because this is how Bitcoins are subdivided. Just like a dollar is a 100 cents, one Bitcoin is 100 million Satoshis. Now no one can remember Bitcoin addresses, and that's the reason why people use wallets. Wallets are softwares that allow you to manage your Bitcoin addresses. So in the real world, Bob would just use his wallet to create a QR code that encodes his address. Then Alice can use her wallet on her phone to scan the QR code, and then her wallet will automatically create a transaction with a transaction number, the input of her address, and the output of Bob's address. Then she only has to specify the amount she wants to send, hit enter, and voila, the transaction is broadcasted to the network. But wait, there is more. The Bitcoin nodes don't just update their ledger with every new transaction, one after the other. Instead, they update the ledger with blocks of transactions. This is why you hear people talk about the blockchain, because the ledger is basically just a chain of blocks that contain transactions. Now, where do these blocks come from? The blocks are generated by mining nodes, which are a special type of node. Mining nodes collect all the new transactions, in this example the transactions 1 through 6. Then they also include a hash value of the previous block, more on that later, as well as a special transaction in which they assign themselves a certain amount of Bitcoin. This is the block reward that they get for creating a new block. But before they can create a new block, they have to find a special number called the nonce. Don't worry if this was a bit much. I will explain all of this later on in greater detail. For now, just remember that the ledger is updated in blocks of transactions. These blocks are generated by specialized nodes, so-called mining nodes. The mining nodes take all the new transactions, assign themselves a block reward, and link the block to the previous block. Then they try to find this special number called the nonce, and if they succeed, the block gets added to the blockchain. Now all the nodes have the new transactions 1 through 6 plus the special reward transaction in their blockchain, and they can calculate the new balances of all participants in the network. On average, it takes about 10 minutes for a mining node to find the special number, the nonce, and so it takes on average 10 minutes for new transactions to be added to the blockchain. Now hold on to your butts, cause shit's about to get technical. To truly understand how Bitcoin mining works, we have to look at the concept of a hash function. But before we have a look at hash functions, we need to go deeper. Actually, we don't have to go all that deep. You probably already know that computers only know zeros and ones. And if you didn't, you're welcome. Now you know. So to translate from humans to computers, we use what's called the ASCII table, where every symbol that you can type or see on a screen has a number in the decimal as well as the binary system. Now if you want to know more about the binary system, you have to look it up on the internet. I will not go into this in this video. But basically every symbol is represented by 8 bits, which is 1 byte, so it's just 8 zeros or ones. So every time you type a capital A, that A is stored as 0, 1, then 5 zeros and a 1 again on the computer, alright? And now with that in mind, we can look at hash functions. So there are different hash functions, but the one that's used in Bitcoin is called SHA-256. And this algorithm of the hash function takes as an input any kind of data. For example, this quote right here. And now remember, every letter is encoded as an 8-bit, so 8 zeros and ones on the computer. So basically the computer just sees a really long list of 8-bit numbers. Then it takes these numbers and does some math magic to it that we will not go into in this video, and creates 256 new numbers out of those that you put into the algorithm. Now these 256 new numbers can also be displayed as the corresponding characters. So if you take the first quote and put it into SHA-256, you get a hash value of C6015 and so forth. Now the hash function has some important properties. The first one we already saw is that it always generates a sequence of 256 random numbers, or in human form, characters. So even if you were to take the Bible and put it into the SHA-256 algorithm, you would end up with 256 random numbers, or in human form 256 random characters. Alright? The next property is that if you change the input just slightly, for example in the second quote, where you have a capital C in cash, you receive a completely different hash value. This is very important because it means that if you see a hash value, it is impossible for you to figure out what you used as an input for the SHA-256 algorithm. This way the algorithm is basically a one-way street. You can put data into it and get a hash value, but you cannot use the hash value and re-engineer what you used as an input for the algorithm. And this irreversibility is the third property of the SHA-256 algorithm. So far so good, but how is this relevant to mining? Well, transactions in a bit more detail look like this. There you can see there's a transaction ID, then the size, so how many bytes make up this transaction, a version, and so forth. This data can also be put into the SHA-256 algorithm, and this is exactly what miners do. They take all the new transactions as well as the hash value of the previous block, plus the special number called the nonce, and then they calculate the hash value of that data. And now let's remember the properties of the hash function. First, they will always receive 256 new numbers, or in human form, characters. Second, we know that each time you change the input slightly, you get a very different hash value. And this is why miners use the special number called the nonce, because all other input data, the transactions, as well as the previous hash value, are static. That means they don't change. And so to get new, different hash functions, they need to add a variable number called the nonce. Now, why do they want to find new hash values? That is because to create a new block that is accepted by other nodes, the hash value of that block with the nonce must start with a certain amount of zeros. This is just a rule of the Bitcoin network, and we can get into why that is later. For now, just remember that miners want to find a special hash value that starts with a certain amount of zeros. And if we now remember the third property, that you cannot find out the input data from the hash value, you realize that the only way miners can find such a hash value is by randomly guessing a nonce and then calculating the hash value. So all miners do is this: they take the new transactions as well as the hash value of the previous block, and then they guess a random number. Then they take all of that data and put it into the SHA-256 algorithm. The algorithm then returns a hash value, and if it starts with the right amount of zeros, the miner has succeeded in finding a new block. This whole process is also known as proof of work, because to find the right nonce that will result in a hash value that starts with the right amount of zeros, miners have to calculate many hash values. This is also why Bitcoin mining takes a lot of energy, and why miners get to include a block reward where they assign themselves a certain amount of Bitcoin if they are successful at finding the nonce. This way they get compensated for the hard work, and they can pay their electricity bills and buy new hardware. Now, speaking of rewards for your hard work, making this video took a fuckload of time. So if you're still watching and if you like it so far, how about you show me some love and send me some sats? Thanks. Alrighty then, moving on. By now you might think, yeah well, this sounds pretty retarded. Why do we need to make blocks and waste all this energy? Why don't we just add transactions to the ledger? Well, it's because of the same reason that most people still haven't sent me some sats. It's because people are greedy. And since every node has its own ledger, some people would simply create fake transactions in which they would assign themselves more Bitcoin than they rightfully own. This is also known in computer science as the Byzantine's generals problem. The problem that Bitcoin faces is this: how do we make sure that all these independent nodes, which have their own ledgers, end up with the same ledger? Or in other words, how do we prevent anyone from cheating? Well, the solution is simple. We make it expensive to cheat. And we do that by using proof of work. So if B wanted to cheat the system and assign itself 420 Bitcoins, it could not just add this transaction to its ledger. It would have to create a block containing that transaction. And as we now know, creating a block requires a lot of energy, which has to be bought with real money. Let's see how proof of work prevents people from cheating by looking at another problem people often talk about, the so-called double spend. In this scenario, Alice tries to cheat the system by spending the same Bitcoin twice. To do that, she creates two transactions. Both transactions have the same address that belongs to Alice as an input, but different output addresses. One is the address of Bob and the other one of Carl. Alice would then broadcast both transactions at the same time to the network. Now, the mining nodes don't just mindlessly include all transactions. They first check them. So, depending on which transaction reaches them first, they would accept the first transaction. But if they then receive the other transaction and see that it uses the same address as an input and that address does not have enough funds to pay for both transactions, they would then reject the second transaction. So in this example, two nodes would think that the transaction to Bob is valid, and the other nodes in blue would think that the transaction to Carl is valid. So essentially Alice has split the network into two. All the mining nodes of Team Red will try to create a block containing the transaction to Bob, and all the mining nodes in Team Blue will try to create a block containing the transaction to Carl. Now, since miners are just randomly choosing numbers as the nonce to find the right hash value with sufficient zeros in the beginning, the outcome of this race is uncertain. However, since the team with more or faster computers can guess much quicker than the other team, they are on average much more likely to find the right nonce first. So let's imagine Team Blue finds the right nonce and then broadcasts the block to the network. All other nodes will verify that the nonce is indeed the correct one that will result in a hash value with the right amount of zeros first, and then they will all update their ledger with that block containing the transaction to Carl. Now the network is in sync again, and since all nodes now accept the transaction to Carl as valid, they will reject the transaction to Bob. Now let's imagine that just by chance, both Team Red and Team Blue find a valid block at the same time and broadcast it to the network. Then the same scenario would repeat. All the nodes that received the block from Team Red first would now continue creating a new block that is referencing this block from Team Red as the previous block, while all the blocks that received the block from Team Blue first would continue creating a new block referencing the blue block as the previous block. This creates what is known as a soft fork, in which the blockchain is temporarily split into two. Now imagine that just by chance, both the red and blue team again find the next block at the same time. Then both teams just add their new block to their blockchain and continue trying to find the next block. Now, since the blue team has more computing power than the red one, it becomes increasingly unlikely that both teams will continue finding blocks at the same time. So eventually the blue team will find the next block first, and with that block they will have the longest blockchain. Another rule enforced by the Bitcoin protocol is that the longest blockchain is always the correct one that is accepted by all nodes. And so in this case, all the miners that were working for Team Red would at this point realize that mining more blocks on the red part of the soft fork is just wasting energy and hence money, and then they would switch to Team Blue and continue adding to the longest blockchain on the left side of the fork. This way, the Bitcoin network always organically converges towards one accepted blockchain that all nodes on the network agree on. These concepts are also relevant when you hear people speak of a 51 attack. In a 51 attack, a malicious actor would try to include a fake transaction into a block. Now, no other mining nodes would accept his transaction, and so he has to try and mine the block all by himself. But to win against all the other miners in the network in this mini hash war to find the longest blockchain, he would need to have at least 51% of the network's total computing power. So if an attacker does not have more computing power than all the other miners in the network combined, he will eventually lose out because he is slower at finding new blocks, and hence his side of the soft fork will be shorter. And this leads us to another important realization. Bitcoin miners are not actually wasting energy, because all that energy is used to prevent attackers from executing a 51 attack. Anyone who would want to attack the network this way would have to have more computing power, which means more hardware and also more electricity than all the other miners combined. Now at this point, all the miners in the Bitcoin network have so much computing power that not even the United States, China, or Russia could attack it with a 51 attack. Alright, remember how I said Bitcoin addresses look like random strings of numbers and letters, but more on that later. Well, it's been quite a while, and so it's time to go back and look at addresses and wallets. If you want to get started sending and receiving Bitcoins just like Alice and Bob, then first you need to get a wallet. Now you can download software wallets from your app store of choice, or you can buy a hardware wallet. Whatever wallet you end up choosing, the underlying principle of how it works is the same. First, the wallet will generate a private key, the one in black in this example. The private key is basically just a very large random number, and so displayed in the binary system it would be 256 random zeros or ones. Just imagine that your wallet simulates 256 coin tosses. Each time it gets head, it writes down a 1, and if it gets tail, it writes down a 0. This way it generates your private key. This way everyone gets a unique private key. The chance of someone getting the same private key as you is the same chance as someone also flipping a coin 256 times and getting the same sequence of heads and tails as you. This probability is basically 0 because there are 2 to the power of 256 possible private keys. Now that number is about the same as 10 to the power of 77. And for comparison, the number of atoms in the visible universe is about 10 to the power of 80. So the chance that someone gets the same private key as you is about the same chance as you and someone else choosing the same atom out of all the atoms in the visible universe. This is very important because whoever has the private key has the ability to spend your Bitcoin. So whatever you do, never let anyone know what your private key is. Now does that mean that you need to remember this random number that consists of 256 random zeros and ones? Fortunately no, because in practice the wallet will generate your private key by picking 12 or 24 random words out of a word list that is known as the BIP39 word list. BIP39 stands for Bitcoin Improvement Protocol 39, and this word list contains 2048 words, where each word is assigned a number in binary. So abandon would be word number 0, and then it will continue all the way down to sue, which would be the last word in the list. So if your wallet asks you to write down these 12 or 24 words, do that and make sure that you do not lose them, because if you lose these words, then you cannot restore your private key and you will lose the ability to spend any of your Bitcoin. Now don't worry, just inform yourself about how to store your keys properly and you will be fine. For example, if you write down those 12 or 24 words 2 or even 3 times and store those at different locations, the chances of you losing all 2 or 3 of them at the same time are very low. So now that the wallet has generated your private key and you have safely stored the 12 or 24 words that are used to generate your private key, we can look at the next step where the wallet will use your private key and some cryptography to generate a public key. Now we will not go into details on this step because it involves a lot of math and it could fill an entire video on its own. Then the wallet will take your public key, here the one in white, and put it into the SHA-256 hash function. This will result in your very own Bitcoin address, to which you can receive funds. Think of your Bitcoin address as something like your bank account number. It's just an address where people can send money to you. Now you can publicize this address freely on the internet, because remember the third property of the hash function. No one can re-engineer your public key, which was the input to the hash function, from the output, which is your address. Now imagine someone has sent you some Bitcoin. Couldn't someone just use your address and use it as an input in a transaction? Actually, no. Because to spend Bitcoin, you don't just need to include the address into the transaction input, but you also need to prove that you are the owner of the private key. And since nobody else knows your private key, only you get to spend the Bitcoins on your address. So in terms of spending, think of your address as a check, that first needs to be signed by you before someone can redeem that check. So how exactly do you prove that you are in possession of the private key? Well, this step also includes a lot of cryptography and would be beyond the scope of this video. Maybe I'll create a future video explaining the cryptography used, but for now just rest assured that as long as no one knows your private key, your bitcoins are safe. Now one last point that people sometimes get confused about. Your bitcoins are not stored in the wallet. Because remember, the amount of bitcoin associated with an address is determined by summing up all the transactions to and from that address. This means that your bitcoins are always safely stored in the distributed ledger of the Bitcoin network, and you only need the wallet to spend funds or generate new addresses. Alright, if you've made it to the end of this video, you should now have a solid understanding of how Bitcoin works. And so,
please clap.